Hello. So let us take the next capsule, the Gramian Revisited. Here we shall prove a very important formula called the Cauchy-Binet formula. It's a remarkable formula and it's valid for for matrices over uh, for matrices over any field, but we shall assume that the matrices have complex entries. In fact, we shall first assume that the matrix has real entries, and from real to complex, it's easy. So let us assume that A is a K cross N matrix and B is a N cross K matrix. Then the Cauchy-Binet formula says the determinant of AB is sum of the K by K principal minors of BA. BA, that is, you reverse the order. So let us write A as W1 transpose da 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 WK transpose, where and B is V1 da 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 VK, where the V's are column vectors, W's are also column vectors. So W transpose are the row vectors. So A is K cross N and B is N cross K. Remember that my vectors V1, V2, VK, W1, W2, WK are columns in Rn. Now, first of all, let us dispose of the uninteresting case when the vectors v1, v2, vk are linearly dependent or w1, w2, wk are linearly dependent. This is an uninteresting case. Let us dispose of. Why is it uninteresting? Both sides are 0. That's the reason why it's uninteresting. So, for example, suppose that w1, w2, wk are linearly dependent. Then what can you say about determinant of AB? You see, I can perform row operations and make one of the rows 0. And on the left hand side is 0. Now look at the right hand side. Sum of the K by K principal minors of BA. Pick one of the principal minors of BA. How do you obtain a principal minor of BA? You have to take B is a N cross K matrix. So you pick up K rows, say Ri1, Ri2, Rik of B. And I want a principal minor. Remember, K by K principal minor. So if I take rows with subscripts I1, I2, Ik from B, then I'll have to take columns with subscripts I1, I2, Ik from A, and then I have to take the product of these two matrices, and I have to take the determinant. That will be the K by K principal minor. So I picked up K. Remember that the row rank of A, is strictly less than K. So any K by K submatrix, will have a 0 determinant. That's why the determinant will rank. The rank of A is strictly less than K. The vectors are linearly dependent. So any K by K submatrix will have 0 determinant. So if I take the principal K by K principal minor of BA, it will be obtained by taking a K by K matrix of B and a K by K matrix of A, multiplying them together and taking the determinant. And you will see that the determinant is again 0. So both sides of this equation star become 0 when the vectors v1, v2, vk are linearly dependent, or when the vectors w1, w2, wk are linearly dependent. I explained this when w's are linearly dependent. A similar argument you can give when the v's are linearly dependent. I hope that part is clear. So you have to take up K by K principal minor of BA and show that is 0. And how do I get a K by K principal minor of BA? I have to take K rows of B, and I'll have to take K columns of A. But no matter what K columns of A I take, that K by K minor is going to be 0, because A has rank strictly less than K. So we are disposed of the uninteresting case. And now in particular, remember, suppose for example, this K exceeds N. Remember the vectors are in Rn. Remember the vectors V, the V's and the W's are in Rn. So if K exceeds N, then we are in the linearly dependent scenario, and namely the uninteresting scenario. So now let us Now let us go to the interesting scenario. Interesting scenario is that V1, V2, Vk are linearly independent. W1, W2, Wk are linearly independent. We are also going to assume case 2. In this particular scenario, we are going to assume that the matrix AB is diagonalizable. AB is a K cross K matrix. We are going to assume that's diagonalizable and non-singular. Case 3, will relax these. We will later see how these conditions can be drawn. First, we will prove it under the more stringent hypothesis that AB is non-singular and diagonalizable. So let's look into this situation. Now, suppose if nu is in the null space of A, that means A nu is 0. That means B A nu is 0. So nu is also in the null space of B. Now, rank of A is how much? Rank of A is K. How many columns does A have? N columns. So what is the nullity of A? N minus K. So I can find N minus K linearly independent elements in the null space of A, which means I have the same number, N minus K linearly independent vectors in the null space of BA. In other words, 0 is an eigenvalue of BA with geometric multiplicity at least K, N minus K, at least N minus K. So the algebraic multiplicity must also be at least N minus K. In any case, we have accounted for N minus K eigen. We have already found N minus K eigenvalues of BA. What are they? 0, 0, 0, 0 counted N minus K times. Now we need to understand the remaining K eigenvalues. The remaining K eigenvalues. Let us call the remaining K eigenvalues mu1, mu2, mu k. The remaining K eigenvalues of BA, let us call them mu1, mu2, mu k. We will show that these very same numbers mu1, mu2, mu-k are also the list of eigenvalues of AB. But now I know the list of eigenvalues of AB. So what is the determinant of AB? The product of eigenvalues, namely mu1, mu2, mu-k. So I have already found determinant of AB, namely mu1, mu2, mu-k. I also have the complete list of eigenvalues of BA. What are they? Mu1, mu2, mu-k, 0, 0, 0, 0, 0. Remaining are zeros. Now, how do I get the sum of the K by K principal minors of BA? Sum of the K by K principal minors of BA is exactly the same as sums of the products of eigenvalues taken K at a time. But now, so many eigenvalues are 0. So if I take a product of K eigenvalues and one of them is 0, then the product collapses. So what I have to do, I have to take K eigenvalues of BA, multiply them together, and take the sum of all possible combinations of these. But the only combination that will give you a non-zero number is mu1, mu2, mu-k. So the sum of the K by K principal minors, of BA is again mu1, mu2, mu-k, and we would have verified that determinant of BA equals the sum of the K by K principal minors of, the determinant of AB is the same as the sum of the K by K principal minors of BA. And the Cauchy-Binet formula would have been verified in this case. So now what is it that remains? We have to now show this claim. We have to prove that mu1, mu2, mu-k, the remaining K eigenvalues of BA are precisely the eigenvalues of AB. That's the only thing that we have to prove. So let us try to produce these eigenvalues, and we'll produce these remaining eigenvalues by actually finding eigenvectors. So we need to find the remaining eigenvalues of BA. We find instead the corresponding eigenvectors. We shall seek an eigenvector in the form C1 V1 plus C2 V2 plus ... CK VK double star. Let us say that the eigenvalue is mu. What does it mean to say that C1 V1 plus ... plus CK VK is an eigenvector of BA? It means BA applied to C1 V1 plus ... plus CK VK equals mu times C1 V1 plus ... plus CK VK. Well, first let us stare at this matrix BA properly. What is BA? Let us go back. Here is your matrix B, V1, V2, Vk, and then here is this matrix A, W1 transpose, WK transpose. BA. Now BA, I can do a block multiplication. Obviously, I'm going to do a block multiplication. And what will be BA? BA will be V1 W1 transpose plus dot 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 VK WK transpose. V1 is a column, W transpose is a row, VW transpose is going to be an n cross n matrix. So BA is a sum of n cross n matrices. What is BA again? BA exactly V1 W1 transpose plus dot 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 plus VK WK transpose. So let us put this in the previous line. Let us substitute this in the previous line. So let us look at the LHS. BA applied to summation CSVS is VLWL transpose CSVS summation over L and summation over S. But CS is a scalar, so it will come out of this. So it will come out right to the left, and we are left with VL WL transpose VS. WL transpose is a row, V is a column, so W transpose V is a real number that can come out. Right? W transpose V is a scalar. There's a typo here. It should not be V transpose V. It is W transpose V. The obvious typo, and you can guess what it is. So I'm going to write this W transpose V onto the left, and I can write. So this equation. So this can be written as W transpose V, WL transpose VS, CS VL. So the left hand side has been written down. Right hand side is mu times C1 V1 plus da 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 plus CK VK. So we got this equation. Summation WL transpose VS CS VL equal to summation mu times CS VS. Remember, the vectors V1, V2, Vk are linearly independent, and so I can equate the coefficients of Vs on both sides or VL on both sides, and this last equation implies summation S from 1 to K WL transpose VS CS is mu times CL. But this WL transpose VS is precisely the LS entry of the product AB. So this last equation reads AB applied to C1, C2, Ck equal to mu applied to C1, C2, Ck. Well, this precisely means mu is a eigenvalue and the corresponding vector C1, C2, Ck is an eigenvector. So we started out by looking for an eigenvector of BA in this form, and where the coefficients C1, C2, Ck, we did not know what they were, but now we know. Now we know what the C1, C2, Ck are supposed to be. Not only that, we also know what the mu is supposed to be. What are they? Mu is supposed to be an eigenvalue of eigenvalue of AB. Mu is supposed to be an eigenvalue of AB, and the coefficient C1, C2, Ck is an eigenvector of AB. But now AB is non-singular, which means that mu is non-zero. So this eigenvalue is different from the previously found eigenvalues. We found n minus k eigenvalues. Remember 0, 0, 0, 0, 0. This is not one of them. And so the count of the eigenvalues, we are not doing any, we are not messing up with the count of the eigenvalues. This eigenvalue cannot be 0. This eigenvalue is a non-zero eigenvalue. How many such eigenvalues are there? Mu1, mu2, mu-k. But AB is diagonalizable. AB, so if mu1, mu2, mu-k is a list of eigenvalues of AB, the corresponding eigenvectors are linearly independent. So we can have k linearly independent sets of coefficients, and each of them is going to give you an eigenvector. And so I'm going to get k linearly independent eigenvectors of BA in this manner. So I have accounted for all the eigenvalues, and so the job is done. And that is exactly what we wanted to prove. So the proof of the Cauchy-Binet formula has been established, but for the special case when AB is non-singular and AB is diagonalizable. Now you may argue that these are very strong conditions. How do I relax these conditions? It's very easy to relax it. Remember that diagonalizability is generic. Invertibility is generic. Non-invertibility is rare. Non-diagonalizability is rare. So if a matrix happens to be a non-invertible or non-diagonalizable, you perturb it ever so slightly, you're likely to make it diagonalizable and invertible. So in other words, a precise way to say this is that there exists a sequence of matrices AM converging to A and a sequence of matrices BM converging to B such that AM BM is non-singular and diagonalizable, and AM BM will obviously converge to AB. BM AM will obviously converge to BA. Since AM BM is non-singular and diagonalizable, the Cauchy-Binet formula is valid for AM BM. In other words, determinant of AM BM equal to the sum of the k by k principal minors of BMA. In other words, the equation star, the Cauchy-Binet, the star equation, Cauchy-Binet formula, holds for A replaced by AM, B replaced by BM on both sides. But look at the equation star. What is determinant of AB? Determinant of AB is just going to be a polynomial in the entries of A and B. Over the right hand side is also a polynomial in the entries of A and B. Polynomial is a continuous function, right? And I have this equation, so this equation star holds for AM and BM, and therefore I write this equation star with A replaced by AM, B replaced by BM on both sides. And I can take the limit of both sides as m goes to infinity, and appeal to continuity, and I can get the validity of star for A and B. That's the way to circumvent the problem. First, you do it for diagonalizable case, and then the rest will follow by a perturbation argument. This argument is so frequently appearing that we are looking at the first instance of we are exploiting the genericity of diagonalizability for the first time. An obvious special case is to take A to be a real matrix and B to be A transpose straight away. Then what will be determinant of AB? It will be simply with the Gramian of V1, V2, Vk. And what will so the Cauchy-Binet formula reads that the Gramian of V1, V2, Vk is same as the sum of the k by k principal minors of A transpose A. Now I want you to write A transpose, and I want you to write A, and I want you to check that the sum of the k by k principal minors of A transpose A is exactly going to be equal to the sum of the squares of the k cross k submatrices of A. Second equality is just, it is obvious. The second equation is obvious, but the first equation follows as a corollary of the Cauchy-Binet, and the second equation is just a simple consequence. Just look at the minors, look at the principal minors of A transpose A, and you will see what I'm talking about. Do it for A to when A is say a 2 cross 4 matrix, for instance. You will immediately get convinced of this. The general case is very similar. In particular, the Gramian is non-negative, something that we have said several times, and now we are able to see rigorously that the Gramian has been proved to be a non-negative. Now let us come to Gram-Schmidt's method and Gramians. Let V1, V2, Vk be k linearly independent eigenvectors. What is the Gram-Schmidt's method? The Gram-Schmidt's method, first we will replace V1 and divide it by the length. Let us assume that is already done. Let us assume that V1 is a unit vector. How do you obtain V2? How do you obtain the second vector? Subtract from V2 the tangential component, right? And you will get the normal component V2 superscript n, and you will divide by the length, and you will get your W2. Then you will go to the next vector V3. You will subtract from V3 the component lying in the plane of the previous two, and you will be left with the normal component, and you have to divide by the length of the normal component. Now, this theorem says that you keep dividing at each stage Vkn by the norm of Vkn. Is there a nice expression for this norm of Vkn? There is. Norm of Vkn squared is a ratio of 2 Gramians. It's a beautiful result, very useful in many applications. And the proof is very easy. In fact, it is being left as an exercise. You want to do it for three vectors v1, v2, v3, go ahead. Go ahead and take k to be 3, do the complete calculation, and you will immediately see that the general case simply follows along the same lines. So let us see how to go about it. What is the normal component? Normal component, you take Vk and subtract off the tangential component. Tangential component means the component of Vk in the space spanned by V1, V2, Vk minus 1. In other words, Vkn is obtained from Vk by subtracting a linear combination of V1, V2, Vk minus 1. Let us coefficients are called C1, C2, Ck minus 1. What does it mean to say that I'm subtracting off component in the tangential direction? It's a normal component. So when I take the dot product of Vk with V1, Vk with V2, Vk with V3, I'm going to get 0 because it's a normal component. So I'm going to get Vkn dot V1 is 0, dot 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 Vkn dot Vk minus 1 is 0 by very definition. But these dot products gives you a system of k minus 1 equations for C1, C2, Ck minus 1. So I would like you to write down these equations for C1, C2, Ck minus 1 and solve them by Cramer's rule. When you solve them using Cramer's rule, remember Cramer's rule for solving systems of equations, you're going to get each of these C1, C2, Ck minus 1 is a ratio of two determinants. And the bottom one, the denominator, is going to be the Grammian of V1, V2, Vk minus 1. Okay. And so what you need to do is that you clear the denominators by multiplying out by the Grammian. You do that. The next thing to remember is that what is this Vk over here? This Vk is going to be Vkn plus Vkt. This factor Vk here can be written as the normal component plus the tangential component. But Vkn dot Vkn gives you norm Vkn squared. Vkn dot with the tangential component is 0. So now you have the expression for Vkn squared, and you have written the right hand side where these constants C1, C2, Ck minus 1 have been replaced by ratios of Gramians. You put that and clear the denominators, and you will immediately get the result. Please do it for k equal to 3. Please do it for 3 vectors v1, v2, v3 and see what happens and convince yourself about this. And then the next is again a little exercise. If you take vectors v1, v2, vk in Rn, the Gramian is always going to be less than or equal to norm v1 squared dot 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 norm vk squared. Equality holds if and only if one of the vectors is 0 or the vectors are mutually orthogonal. Without loss of generality, let us assume that the first vector is a unit vector v1. And it is clear that if one of the vectors is 0, both sides are going to be 0. Uninteresting case. So let us set aside this uninteresting case. Okay, so assume that the vectors are all non-zero. Further, I can divide both sides by norm v1 squared, and I can assume that v1 is already a unit vector. That also I can assume. If the vectors are linearly dependent, left hand side is 0, right hand side is strictly positive. So again, the inequality is completely trivial. So I may jolly well assume that the vectors are linearly independent. And I'm going to, if I apply the Gram-Schmidts to this, I get W1, W2, Wk. But W1 is the same as V1 because V1 is assumed to be a unit vector. Now remember, what exactly happens to this when the vectors are mutually orthonormal or orthogonal unit vectors? The Gramian of orthonormal system is 1. So both sides are 1 when the vectors are mutually orthogonal and unit vectors. In other words, Gramian of W1, W2, Wk is 1. But W1 is the same as V1, remember? So Gramian of V1, W2, da da da, WK is 1. But now but what is W2? Remember, how do I get W2? I get it from V2n by dividing by the length. So multiply this equation, the second equation, by norm V2n squared. Then you'll get Gramian of V1, V2 superscript n, comma, W3, etc., WK is going to be norm V2n squared. But the normal component of V2 squared is going to be less than or equal to norm V2 squared. When will the length of a vector equal its normal component? When there is no tangential component. When will that happen? When V2 and V1 are orthogonal. So equality holds here if and only if V2 and V1 are orthogonal. Now let us make this W3, convert this W3 in terms of V3. Multiply by norm V3n. Multiply by the norm V3n squared. So again you will get Gramian of V1, V2, V3n, comma, W4, da, 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 WK. W4, W5 and all I'm not touching right now. I will tamper with it in the next step. What do you get? Right hand side you get less than or equal to norm V2 squared into norm V3n squared. But norm V3n squared is going to be less than the norm or the normal component of V3 is going to be less than or equal to the norm of V3. But when will the normal component norm equal to the length of the vector? When there is no tangential component. When will there be no tangential component? If and only if V3 is orthogonal to the plane spanned by V1 and V2. So equality holds here if and only if equality holds earlier and equality holds at two places. Equality holds earlier means V1 is orthogonal to V2. Now we want V3 to be orthogonal to V1 and V2 both. In other words, V1, V2, V3 must all be mutually orthogonal. So proceeding thus, we get that the graph. So we keep continuing like this, and we would have proved the result. And so this is a very simple exercise. Geometrically, the Grammian, I said this several times, it is the volume of the parallelepiped given by these k vectors. And when will the volume of the parallelepiped equal the product of the lengths of the sides if and only the parallelepiped is a rectangular box? That's the geometrical meaning of this exercise. A very special case is that when k is n, when there are n vectors in Rn, then the Gramian is simply, what you do is that you take the vectors together, v1, v2, vn, and make an n cross n matrix. And the Gramian is simply the determinant of the matrix squared. And that statement is noteworthy special case. The noteworthy special case is if A is an n cross n matrix with real entries, then determinant of A squared is determinant of AA transpose, namely the Gramian of the columns V1, V2, Vn. And so, and by the previous inequality, we get that the determinant of A the whole squared is less than or equal to norm V1 squared dot norm Vn squared, where V1, V2, Vn are the columns of A. Equality holds if and only if the columns are orthogonal or one of the vectors is 0. And I already given you the geometrical interpretation of this. Of course, this can be further generalized. I can take two sets of vectors, V1, V2, Vk, W1, W2, Wl. Now the Gramian of V1, V2, Vk, W1, W2, Wl is less than or equal to the Gramian of V1, V2, Vk times the Gramian of W1, W2, Wl. When will equality hold? Equality holds if at least one of the sets, W1, W2, Wl or V1, V2, Vk is linearly dependent. That's one situation. Other situation is that each Vi is orthogonal to each Wj. For each pair ij, Vi and Wj are orthogonal. These are the cases where the equality will hold. And so I think with this, I will stop this capsule